Okay, hi everybody. So now we are shifting gears and we're going to talk about my expertise, I guess, if you want to call it that. I was gonna say my favorite thing, but that's very morbid and it's not. It's not where I want to be right now. We're gonna talk about global warming. So this is part one of two. This part is more of a historical sort of a historical survey of our knowledge of climate change and global warming. And then next week we'll do more of like what's happening and also the controversy of it. We also typically watch a film during this lecture. I'm going to show that film to you during the Zoom tomorrow because it's on Amazon. You have to pay for it, but I paid for it, so um, I want to show it to you, and the only way we can do that is if we're live, I guess, because if I put it in here, then I'm going to have the copyright thing again. Anyway, I'm rambling. We'll work it out. We'll work out the details. Let's talk about global warming. So, how long have we known about the ideas behind our understanding of climate change? Turns out a really long time, dating back all the way to this guy, Svante Arrhenius, who was a Swedish scientist and a physical chemist. He won the Nobel Prize actually in 1903 for this equation, which doesn't have isn't exactly what we're going to be talking about here, but he was just a very well-known, sort of famous old white guy. But in 1896, he wrote a journal article, which he published in the Philosophical Magazine and Journal of Science, called On the Influence of Carbonic Acid in the Air Upon the Temperature of the Ground. Basically, outlining the principles behind what's causing our current climate change. In this case, carbonic acid is referring to carbon dioxide. And so he was looking at the end of the 19th century, right? So 125 years ago, the idea that humans emitting all of these greenhouse gases, carbon dioxide, methane, etc., were potentially causing a warming, which we now know is climate change and global warming. So his conclusions were basically this article, sorry, let me just move myself around. This article quantified the greenhouse effect. And we haven't really talked specifically about the greenhouse effect, so I have some slides on that in a second. Some of you may be familiar with the greenhouse effect and what it is, so this will be a review for you all, but nevertheless, this article also speculated about whether long-term changes in carbon dioxide in the atmosphere, which again Arrhenius called carbonic acid, have contributed to variations in climate over time. And this article essentially created the case for global warming by explaining the physics behind, the sort of chemical physics behind how sorry, my partner is like trying not to be in the video, but needed something over here. Anyway, the chemical physics behind how carbon dioxide causes temperature changes. So he didn't explicitly suggest that burning fossil fuels would cause global warming, but it's clear that he is aware that fossil fuels are a significant source of carbon dioxide being emitted by humans. And later on in his work, he does more explicitly suggest the link between fossil fuels and climate change. So I do want to say that the history of climate science and the trajectory of our understanding of climate change is a process. And this just begins the process in 1896. But that was a long time ago. So I want to really stress that this isn't a new idea that we have. So following... It's really like a game where I can move my video so you can follow me. Following Arrhenius, lots of people started thinking about this. Again, these people, though, were not climate scientists, as you might think of, for example, me as being a climate scientist. They were geologists, meteorologists, chemists, physicists, that sort of thing, okay? So we have Chamberlain, who was a geologist and was the first to sort of link glacialization, which is like the Ice Age, right, to changes in atmospheric gas concentrations, namely carbon dioxide. Ekholm and other scientists studied sort of the differential heating rates between the poles and the equator and how heat moves between them. And he identified carbon dioxide as an important atmospheric gas. So people are starting to think about this in the early 1900s. And so then I need to kind of refresh and explain what the greenhouse effect is. Now, I don't have time to go into it in extreme detail, but if you take my climate change course, then you'll get the elongated version of this. But essentially, the planet is regulated by incoming and outgoing radiation. Radiation is just energy, heat, typically, heat, energy. So energy comes from anything that has a temperature. So the sun has a really hot temperature, gives off a lot of energy, a lot of radiation, reaching the Earth in the form of visible and ultraviolet, typically. Most of that is absorbed. 30% of it is reflected. The part that is absorbed then gives the Earth, the actual rocks of Earth, a temperature. And then Earth has a temperature, so it also radiates, gives off energy, right? So Earth radiates its own energy, but that radiation isn't invisible light or ultraviolet light. It's an infrared light or infrared radiation, we typically refer to it, which is a slightly less energetic, longer wavelength radiation. And so that radiation then leaves the Earth, goes up into the atmosphere, where it is intercepted by very specific gases. And those gases we call greenhouse gases. They are carbon dioxide, methane, nitrous oxide, water vapor. They absorb that energy that's coming off the Earth. They have nothing to do with the sun, only the energy that's coming from the Earth. They absorb it. They emit it all different directions, but since most of them are close to the Earth, most of that radiation comes back down to the surface of the Earth. This is just a refresher of the electromagnetic spectrum. This is the radiation spectrum. So you can see that most of the sun's radiation is in the visible and ultraviolet range. Most of the Earth's radiation is in the infrared range. So they're slightly different wavelengths and amount of energies. And that's important because carbon dioxide, again, does not interact with radiation coming from the sun. Only radiation coming from the Earth. So in further detail here, what I just said, incoming radiation, you can read through this slide if you want. 50% of it or so is absorbed at the surface, 20% absorbed in the atmosphere, and 30% of it is reflected. It's reflected by bright things like snow and ice, desert, sand, and clouds. Very bright, white sort of things. Okay? And then, as I said, Earth assumes the temperature after it absorbs all that radiation from the sun. Therefore, it emits its own radiation in the form of infrared or long wave or terrestrial radiation going the other direction. So you have in minus out. I'm going to skip this slide here. Sorry. Got to clean these up. It's just like we're in class, awkwardly going through slides that are old. So that radiation coming up off the Earth, again, is intercepted by the blanket of greenhouse gases in the atmosphere, carbon dioxide, nitrous oxide, water vapor, methane. Think of it actually literally like a blanket in the winter. So when you're cold in the winter, you put a blanket on. The blanket, what it does is the heat coming off your own body is intercepted by the blanket and then re-emitted back down to your own body to keep you warm. If you need to get warmer, then you need a thicker blanket or another blanket. And that's what we're doing with climate change. We're putting a thicker blanket on the Earth. I apparently have lots of visualizations of the greenhouse effect. The greenhouse effect. Here's a good one. I like this one. There's also an activity that you can do, which obviously we are not going to do, but I will send you the YouTube link of someone who's doing it, and you'll see that you can replicate the greenhouse effect in your own house using a 2-liter bottle, some Alka-Seltzer, a little bit of water, and a thermometer. Carbon dioxide is very effective at trapping radiation in the infrared part of the spectrum. That's important to remember. All right. So now that we've done that little refresher on the greenhouse effect, and if you have questions, like we'll answer them tomorrow in the Zoom. Let's move forward in the history of our understanding of climate change. So around 1900, Knut Ångström discovered that even tiny concentrations of carbon dioxide absorb lots of radiation in the atmosphere, right? So you don't need that much, just a little bit. Fast forward, 1927, we started emitting fossil fuels during the 1800s. More on this in the next lecture. By 1927, the emissions from fossil fuel burning, from industrial burning of coal mainly, reached 1 billion tons per year. We're now at about 12 billion tons per year, just for reference. But between like the late 1800s and early 1900s and 1938, there was a little bit of a break in our sort of understanding of climate change and climate science. During that time, meteorology became kind of a field. And so people were kind of focusing on weather forecasting during that time and other things. By 1938, a seminal paper written by Guy Callendar showed that temperatures had risen over the previous century. He used thermometer data from the previous 100 years or so to show that the temperature of the Earth had already gone up. And he showed, using calculations by hand, that carbon dioxide concentrations as a result of fossil fuel burning from industry had increased over the same period, and suggested in this paper that this is what caused the warming. Here's the paper by Guy Callendar. Guy Callendar is referenced in this paper as a steam technologist, which is interesting. But the paper, The Artificial Production of Carbon Dioxide and Its Influence on Temperature, is shown here, published in 1938. In his conclusion, he argued that the radiation absorption coefficients of carbon dioxide and water vapor are used to show the effect of carbon dioxide on sky radiation, basically showing the greenhouse effect through observational evidence. So using the increase in temperature that he observed from thermometers, he found that the temperature of the Earth had risen at a rate of 0.005 degrees C per year for the last 50 years. Then he did some calculations using the amount of carbon dioxide that was in the atmosphere, and he estimated that that amount of carbon dioxide would have theoretically raised the temperature of the Earth by 0.003 degrees Celsius per year. So they lined up fairly well. And so he was the first person to suggest this. He drew this figure before we had computers to draw our figures for us. And what this figure shows is his physical sort of calculation of how much carbon dioxide in the atmosphere could influence the temperature. So he has it shown here in carbon dioxide of parts per 10,000. We now talk about carbon dioxide in parts per million. So you just have to add 2 zeros to all these to kind of equate it to the way we refer to things now. So I don't know if you've seen in the news or what, but carbon dioxide concentrations in the atmosphere now are about 410 parts per million. So somewhere in this area over here. So that would align to, according to his calculations, about a degree of warming, a little less than a degree of warming, since the present temperature of when this paper was written. And that's honestly about what we've observed. So he did this all sort of by hand, just using our understanding of radiation and how carbon dioxide interacts with the temperature. And while this is not a very sophisticated calculation, it's still somewhat relevant, actually, and still pretty uncanny in how accurate it is. So this was derogatorily referred to as the calendar effect, and he was widely mocked and dismissed by most meteorologists and weather scientists during the 1930s and 1940s. People were laughed at him, and it was kind of a joke, which sucks because he was right. Until the 1950s came along. And in the 1950s, something very amazing was invented. And this is the part in class where I would ask you what became ubiquitous and useful. Invented is not the right word, but in the 1950s, and the answer is the computer. So prior to the 1950s, computers were actually human beings doing calculations. They were called computers. I don't know if any of you have seen the movie Hidden Figures, but all of the women in that movie were referred to as computers. But in the 1950s, we actually had like a computer, like what I'm recording this on, which could do mathematical calculations in a much faster time frame than a human being could do it, obviously. And so these numerical experiments that were done using computers really advanced the field of climate science in a way that was necessary for us as we came to more and more understand how complex and how complicated the Earth was, that it wasn't just about radiation, it was about all these different things. So here's a paper from 1956, The General Circulation of the Atmosphere, a numerical experiment talking about how we use models and computer simulations to say something about the climate and about climate change. And then in 1955 and 1956, the seminal paper, which you will read as part of your as part of this class, was written by Gilbert Plass and published in a very what's the word, like easily accessible pop science journal of the American Scientist. So it was like easily digestible by the general public, called The Carbon Dioxide Theory of Climatic Change. And you will read this paper with annotations by two contemporary climate scientists. And he wrote in this paper that if you were to double the amount of carbon dioxide that was in the atmosphere, that would result in a rise of 2 to 4 degrees Celsius temperature, a temperature rise of 2 to 4 degrees Celsius. So that's crazy because despite the incredible advancements that we've made in the field of climate science with computer simulations and understanding different cycles and all sorts of things, this estimate is still very much within the range of current estimates that we have. We estimate that with climate change, in the next 100 years or so, we are likely to see 2 to 4 degrees C rise in temperature. So yeah, as you'll read in the paper, even though Gilbert Plass got it right and did understand a lot of the physics, some of this was luck. But that doesn't diminish the fact that in 1956, we had a very complex and thorough understanding of how carbon dioxide in the atmosphere can cause a steep rise in global temperatures. So that was, for those of you doing the math at home, how many years ago? 42, 65 years ago. The field of climate science already basically understood that if we increase and continue to increase the amount of carbon dioxide in the atmosphere, we are going to see the temperature of the planet go up significantly, 2, 3, 4, maybe more degrees Celsius. And we are now seeing that happen. So Gilbert Plass, among many other contemporaries, as you've seen, all the way from Svante Arrhenius through Gilbert Plass, predicted this, talked about this, wrote about this, published on this. It's not a new idea that global warming is real. Okay, it's 65, 125 years old. Okay, it's a very old concept, and we are continuing to understand more about it. We're continuing to improve our forecasts and our projections and understand more complex processes and how the Earth works. But we understand fundamentally that carbon dioxide in the atmosphere, as a result of fossil fuel burning, is causing climate change. So don't let climate deniers convince you that this is just like a liberal hoax. Okay? This is something that's been around for a long time. There are many scientists that have worked on this over many, many decades, centuries really, at this point. Okay. Love this quote by Roger Revelle in 1957, okay, 63 years ago. Human beings are now carrying out a large-scale geophysical experiment. In fact, we are. And Dave Keeling was one of the first people, was the first person actually, to go out and make systematic periodic measurements of the amount of atmospheric carbon dioxide. This data set that he started in 1958, okay, so 2 years after Gilbert Plass's paper, continues today. And what he did is he went to the top of Mauna Loa on the Big Island of Hawaii, and he put an instrument up there which ingests air from the atmosphere. Okay, that air is then run through a few chemical processing equipment, and you get a reading of how much carbon dioxide is in the atmosphere. And the reason that he went to the top of Mauna Loa is because it's a very high mountain. It's in the middle of the ocean. And so it is considered the cleanest atmosphere that could exist, really, right? So if you put it on the top of the Sears Tower, you're going to get lots more carbon dioxide because it's emitting literally from here, from our factories. But if you go to the middle of the ocean and you take these readings, presumably you're getting a reading of what the clean atmosphere is. And so as you can see from this data set, beginning in 1958, continuing all the way through today, so Dave Keeling passed away, but his great-nephew is still running this data set on the top of Mauna Loa through Scripps Institute of Oceanography in San Diego. The carbon dioxide reading when Dave Keeling first went out there in 1958 was about 315 parts per million, which means that for every million molecules of air, 315 of them were carbon dioxide. So it's a pretty small amount, 315 out of every million. Now the number is about 410. This figure is a little bit old, but in 2018 it was 406. I think recently it got up to 415 as the high, and then it kind of, every year it goes through like a cycle because of the trees. The trees lose their leaves and the carbon dioxide in the atmosphere goes up. Then the trees grow their leaves back and the carbon dioxide in the atmosphere goes down because they take some of that carbon dioxide out. But the point of this ramble is that in 1958, Dave Keeling went to the top of Mauna Loa, and 4 years later, he had accumulated enough data to say with unequivocal proof that carbon dioxide concentrations are rising. The only explanation for that is the emission of carbon dioxide from fossil fuels. Okay, so now we have observations to back up Guy Callendar, to back up Gilbert Plass, to test whether ARRHENIUS Arrhenius's explanation of the greenhouse effect is correct. Okay, this is all because of Dave Keeling. And you can go and you can see this curve. They update it every day. If you just Google like Keeling curve, or go to this website, you can actually see what the carbon dioxide concentration is today. I think they do like daily, hourly, maybe hourly or daily. They aggregate a little bit, but they're taking lots of measurements all the time with the equipment up there. Okay, so I mentioned that models and computers were really important. Here's a timeline of how we really came to understand all of the nuances of climate change. So at the very beginning, you have Arrhenius with his greenhouse gas, greenhouse effect model, which we call a radiative transfer model, just looking at radiation in and out and how carbon dioxide intercepts that and interacts with that. You've got CALLENDAR, then you have Plass and Keeling come along in the 1950s, 1960s, when we started to understand things like nonlinear fluid dynamics, which is an integral part of how we forecast the weather, for example, the hydrological cycle, how water vapor in the atmosphere is changing and can change in response to various things. And so we started to put all these things into what we call a climate model. A climate model is just a bunch of mathematical equations written out in code, and then you essentially hit go on the computer, and then it simulates the climate using a bunch of equations, right? So we have equations representing how the wind blows, and we have equations representing the sun, and we have equations representing the trees and the water and the rain and everything. And then in the 1970s, we started to incorporate into these climate models things like sea ice, land surface roughness. In the 1990s, atmospheric chemistry. In the 2000s, aerosols and vegetation. I actually worked on a very small part of the American National Oceanic and Atmospheric Administration model, climate model. I looked at how aerosols, particulates emitted from wildfires, interact with the climate system in the Earth. Okay, so we went from these energy balance models, these radiation models, to what we now call, I guess it's like this backwards. So we went from radiation transfer to Earth system models, which is what we have now. Big, millions of lines of code climate models, which we use to forecast the climate. And we'll talk about the details of that in the next lecture. So what is global warming? Global warming is just the word we use to refer to the observed increase in the surface temperature of the planet. So I'm sure you've seen figures like this. Each of these red dots represents 1 year average global temperature, right? And it's presented in this case as an anomaly, which is basically just taking like a normal temperature, which I think for this one is usually 1940 to 1980 average. That's 0. And then looking at how far away each year is from 0. It's fine to just use the actual temperature, but then these numbers would be like, 18 degrees Celsius, because the average temperature of the globe is 18 degrees Celsius. So it's just easier to take an anomaly to see how far away you are from the normal. So you can see that we have observed about a 1.2 degree global warming Celsius, or about 2 degrees Fahrenheit, since 1860 or so, 1850. So 1.2 degrees Celsius of warming. That's global warming. Obviously, there are lots of other things involved, which we'll talk about. We don't have a ton of time to talk about it, but in my climate change classes, we talk about this like very extensively. But the gist of it is that the globe is warming, which is why we call it global warming. We're going to talk a lot about climate change as a scientific controversy, because that's sort of the point of this class, is to talk about science as controversies. And so a lot of people say that in the 1960s and the 1970s, the globe wasn't warming anymore, it was actually cooling, and they call this like the global cooling scare. And the quintessential climate denier will always point to this and say, Global warming is not real because 50 years ago you guys were saying that it was global cooling. The thing is, we weren't saying that. Some people were noticing that the temperature was not rising as quickly in the 1960s. That before then, from 1890 through the 1940s, global temperatures were increasing. There was slight cooling or stabilizing from the 1950s to the 1970s. It got some people thinking about the next coming ice age, but that was still like 10,000 years away, so no one was seriously saying it's happening right now. Climate deniers will argue that there was a scientific consensus that Earth was cooling in the 1970s, but this is not true. This figure here shows all of the papers, the published journal articles written by scientists from 1965 through 1979 about the climate, and the proportion of them that were written about climate cooling, climate warming, or just sort of neutral articles about the climate. And you can see that there are very few published journal articles about global cooling. One in 1967, two in 1971, another in 1972, and then a couple scattered here and there. But the majority, vast majority, of scientific articles being published in the 1960s and the 1970s were not about global cooling. They were about global warming, because global warming has always been the concern. Global warming has always been understood, and we've always been talking about global warming. Yes, there were some articles that talked about global cooling in the context of an ice age, or maybe that warming had stalled in the 1960s, but this was far from a consensus that the globe was cooling and global warming wasn't happening. We were always talking about global warming. We were always convinced that global warming was happening. So there's this paper here which aggregates that, the myth of the 1970s global cooling scientific consensus. It is not a consensus at all. It was a myth, and it's not true. If you have any climate deniers in your family who bring this up, I am happy to give you more evidence that it is not true that scientists were saying the globe was cooling in the 1960s and 1970s. Okay, fast forward to 1975. Wally Brooker, who actually just passed away recently, a really well-known climate scientist, was actually the first person to use the phrase global warming for the first time in 1975. So most people think global warming came first, then we started using climate change because it's politically correct. We were actually calling it climate change, as you saw, Guy Callendar, Svante Arrhenius, Gilbert Plass. So this article written by Wally Brooker, Climatic Change, Are We on the Brink of a Pronounced Global Warming, is the first time that someone used the phrase global warming. And I personally like the phrase global warming better than climate change, personally. I think it sounds more scary. All right, so let's walk through this timeline then since basically 1980. So we're kind of moving through time space here. So at the end of the 1980s, the IPCC. Oh wait, actually, I'm going to start with this. These slides are out of order. In 1979, the World Meteorological Organization held the first World Climate Conference in Geneva in 1979. This got people thinking on the international stage, and the United Nations eventually convened the Intergovernmental Panel on Climate Change, the IPCC, in 1988. And it was formed specifically as a subsidiary of the United Nations to investigate climate change. In 1990, the IPCC, this new body that had just formed, produced the first assessment report about the global climate, which estimated that global temps had risen by that point, by 1990, about 0.5 degrees Celsius, and that humanity's emissions were adding to the already existing greenhouse gases in the atmosphere, and that the result was going to be more and continued warming. 1990. 1997, the Kyoto Protocol was negotiated, the goal of the Kyoto Protocol was to reduce emissions between 1997 and 2012 by 5% global emissions. And then in 1998, Michael Mann, who is very prolific on Twitter, I follow him, published the hockey stick graph, showing that for the last 1,000 years, temperatures were very, 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 very steady, and then they spiked. Looks like a hockey stick on its side. And so that was enough evidence for a lot of people to say, this is a problem, we should do something about it, let's enter Kyoto. Of course, George W. Bush removed the United States from the Kyoto Protocol, from the treaty. A lot like Trump removed us from the Paris Agreement. Bush was also very active in censoring a lot of climate scientists in the 2000s. If they talked about climate change, very much like similar to the situation with Donald Trump right now. In 2007, the IPCC published another assessment report, the third one, that concluded that humanity was more than 90% responsible for climate change. There are a lot of politics involved here, which I will discuss with you tomorrow in the Zoom. I don't want to take up your time right now. In 2009, there was a little dust-up with ClimateGate where they uncovered a couple emails from between climate scientists, and deniers kind of said that we were all lying. I don't know, it was really silly, dumb. You can Google it. But it was just, part and parcel of the whole saga of the controversy of climate change. Then in 2012, the Arctic Ocean recorded its lowest summertime sea ice concentration. Record low. And in 2013, the Mauna Loa Observatory, the Keeling curve, went above 400 parts per million for the first time since measurements began, and presumably for the first time in several million years. So we have more carbon dioxide in the atmosphere now than we have for at least the last 5 million years, probably the last 15 million years. In 1988, climate scientists and experts also testified in the U.S. Senate about global warming. And one of those scientists, James Hansen, who is also still alive, retired, was censored by George W. Bush, was very vocal about it, and has been really like an idol of mine and many climate scientists. I had the privilege of meeting him. He's actually like a really boring public speaker, but a really, really, really great and important climate scientist. He testified to Congress using his climate model, right? We discussed climate models a couple minutes ago, forecasting what was going to happen with global warming. And he testified, it was on the front page of the New York Times, global warming has begun, expert James Hansen tells Senate. And what he predicted was, using his models, which is still we use today, that the globe would warm by 2020 about 1.2 degrees C, and it has. It has. His model was a little bit too sensitive. We've obviously made refinements to models where we can now pinpoint things with incredible accuracy. His was a little sensitive to the effect of carbon dioxide, but that's, that's science. That's an important part of science, is being close and understanding what was wrong. Nevertheless, I think that his model was still impressively accurate. Even now, despite decades and decades of modeling advancements. Okay, and we obviously have this figure on the right here shows, so his model ended in 1988 or so like around here, and then he forecasted 3 different scenarios going forward into the future. And then you can see that looking back, we can actually look at his forecast and superimpose the actual observations on top of that, and you can see that we've lined up pretty much with his scenario B, which was like a middle of the road scenario. His scenario A, the red line here, was a little bit too sensitive.
Sorry, I didn't quite catch that.
Sorry, I think my Siri just went off.
It's no problem.
So so after, is that my Siri? So after his testimony in 1988, which inspired a very famous climate scientist, climate activist, who happened to be in the Senate, a Mr. Albert Gore. After his testimony, it also created a renewed push to understand climate change and really understand like the specifics of it. And at the same time, it also sparked a resurgence, or actually a manifestation of very extreme climate change denialism. That really was a phenomenon that began at the end of the 80s and now is like reached a fever pitch, especially in the 2000s and the early 2010s. Climate denial was a hot ticket item. So let's talk about that, because climate deniers will often say things like there is a debate among climate scientists about climate change. There is not a debate. There is a consensus. 97%, you'll see that number thrown around a lot, 97%-ish of climate scientists agree that climate change is real and happening because of human-caused fossil fuel emissions. This is a figure from a study. I forget the year that this came out, about 10 years ago or so, 5 years ago, that looked at other studies that looked at whether there was a consensus. And what it found was that all of these other studies showed that there was more than 90% consensus among climate scientists that global warming was real and happening. In fact, this Naomi Oreskes study showed 100% of peer-reviewed articles written about climate agreed that climate change was real, was happening because of human emissions, and was likely to continue. This paper, which I will show you a quick YouTube video of the summary of as well, showed that the scientific agreement and the consensus was highest among climate scientists who scientists who are experts in climate science. Okay, so the less expertise you have in climate science, the less likely you are to agree that humans are causing global warming. Why should we trust those scientists if they don't have expertise in climate science, though? This is a real problem and is touched on in the Merchants of Doubt video, which I am going to show you tomorrow in the Zoom. Okay, so you can see that low expertise in climate science results in a low scientific consensus. The higher expertise, the higher the consensus. Okay, and here's the video, which I am going to show you really quick before we go.
"97% of scientists, including, by the way, some who originally disputed the data, have now put that to rest. They've acknowledged the planet is warming and human activity is contributing to it."
A survey of thousands of scientific papers that took a position on climate change found that 97% endorsed the position that humans are causing global warming.
So 97% of scientists who have written in peer-reviewed journals say the following: climate change is real, it is significantly caused by human activity.
97% of scientists the world over have said that climate change is urgent and man-made and must be addressed.
For over a decade, study after study has found that 97% of publishing climate scientists agree that humans are causing global warming. But what do the general public think? I'm here at the Brisbane City Mall to find out. What percentage of climate scientists do you think agree that humans are causing global warming?
95%, probably 50%.
75%, I think.
80%, yeah.
85.
Would you like to know who was closer then?
I think I was closer.
100%.
Between 5 and 10%?
Not a lot.
Oh, hang on, sorry, other way around. 95%, but split 50-50.
I would say 80%.
95%.
I would say 50.
Off.
There's a huge gap between what many of the public think about the scientific consensus and the actual 97% agreement among climate scientists. Why is there such a large consensus gap? One contributor is misinformation.
The 97% figure that's thrown around, the head of the UN IPC said that number was pulled out of thin air.
That 97% number, that's been debunked in several studies.
This 97% is essentially pulled from thin air.
The stat about the 97% of scientists is based on one discredited study.
97% of all scientists believe...
Is this a bogus number?
It's so not a bogus
It's
number.
so a bogus.
Okay, yours is, mine is, yours is, mine.
From clips like this, you'd think there's a vigorous debate about whether scientists agree that humans are causing global warming. We're often exposed to contradictory messages in the media. How do we see through the misinformation and get to the truth about consensus? I joined with scientists who authored 7 of the key studies into the consensus on climate change. When we looked collectively at the wide range of consensus studies, we found that the expert scientific consensus on human-caused global warming is between 90 to 100%. The higher the expertise in climate science, the stronger the agreement on human-caused global warming. When you get to climate scientists who have published peer-reviewed climate research, there's 97% agreement. But the fact that consensus gets stronger with higher expertise is exploited by those looking to cast doubt on the consensus. They do this by selecting groups of scientists that have lower expertise in climate science to get a lower level of scientific agreement and argue that there's no consensus. Using non-experts to cast doubt on the expert consensus is a key characteristic of science denial known as the appeal to fake experts. This approach was employed by Richard Toll in a comment criticising the 97% consensus. Toll misrepresented a number of consensus studies portraying non-expert groups as representative of the expert consensus. The scientists who authored those studies were none too happy with how their research was misrepresented. But on the positive side, Toll's misrepresentation of all those studies brought the authors of 7 key studies together to publish a full view on the scientific consensus on climate change. Our paper established a consensus on the consensus being between 90 to 100% expert agreement on human-caused global warming, with a number of studies finding 97% consensus.
Okay, so that that figure at the end there, or towards the end, the characteristics of science denial, that's an important figure that I am going to talk more about in the next lecture. And I'm also going to, this is a little preview, I'm also going to talk about briefly what we've observed in terms of global warming, and what we expect to see going into the future, as well as a bit about this climate science denial. And hopefully we'll have a vigorous debate about why people deny global warming, why people deny science in general, and how we fight against that. All right, so I kept this one under an hour. I didn't have a ton of mishaps, so I feel good about it. Anyway, all right, so I will, looking forward to chat with you all in the Zoom. All right.